yo. So, in this video, I'll be going over how to do one of the problems in your Unit 8 multiple choice sets or whatever, where we're discussing combining a solution with a strong acid and a solution with a strong base and what will happen to it and how you can solve for this kind of situation. So, let's go through the question actually. So, the specific question here is where a student combines a solution of strong acid. Notice that it's strong because it's HNO3, which is part of your So I Brought No Clean Clothes. And we have a solution of strong base. Note it's an ionic substance where it has an OH minus. That indicates it's a strong base. And so we have these two solutions, and the student combines them, creating this combined solution. And so in this combined solution, it's asking what the exact pH will be closest to with the options here. And so whenever you have these kind of problems where you have a strong acid reacting with a strong base, you would usually want to write the molecular equation. And so with this, you notice that the strong acid and the strong base react where the H donates to this and creates H2O with KNO3 left over here. And as a quick note, because it's strong acid and strong base, they fully ionize, and so you can actually write the net ionic equation, that being this. That being this. And this is because strong stuff can fully ionize, you can actually just write as the main parts of them, that being the H plus and the OH minus, and the main thing is it creates water, because that's usually how what they usually create. Now, this is all important because you can notice that whenever you have anything that's strong on the reactant side, okay, it will always result in a forward reaction only. I'll make it clear again. If one of the reactants is a strong substance, it is a one-way reaction. There's no backwards reaction that we write. So, because this is strong and this is strong, well, it could have been either one of them had to be strong at least, then it's one-way reaction. And if you recall from Unit 4, a one-way reaction, if you want to find how much of the products and how much of the reactants there are, you use stoic, where you focus on moles. And because it's considering moles and not concentration, what you want to do with this is you want to find the moles of both the acid and the base at the start first. And so let's do that. Using your volume and concentration given for each solution, you result in the moles being resulting in this. So make sure that you remember how to convert from concentration to moles using your liters. And remember to convert to liters and not keep them as milliliters as the problem has it. So because it's 300 milliliters for the first solution, you would just divide by 1,000 milliliters to get 0.3 liters. And then this will give you the moles for your strong acid. And then you can do the same thing. You can do the same thing for your strong base. That being, this is the concentration, this is the liters, voila, multiply on both sides, and this gives you the moles. Now, the point of doing this was because now you have the moles of the strong acid and the strong base, so the reactants, and now you just need to find the limiting reagent. The limiting reagent, if you don't remember, is just the reactant that is the lowest amount needed. Is the whatchamacallit? Oh my god. It's basically the maximum amount of reactant you can use before the one of the reactants runs out. And so you just need to find which one runs out first. And because it's a acid-base reaction, typically because all the coefficients are 1 to 1 to 1 to 1, you can actually just choose which one has the lower amount of moles. And so, in this case, by observation, this one is the limiting reagent. And so, let's get into how that's important to the overall calculations. Remember the balance equation we have earlier? Because we have 0.015 moles of our strong acid and 0.016 moles of our weak strong base, what we want to do is we just want to see how much they would decrease as the reaction goes. Because this is the limiting reagent, this will just go all the way down until it reaches 0 moles. Pretty nice. But because this is not the limiting reagent, but the excess reagent for the strong base, this will just decrease by however much the limiting reagent decrease. So because this one decreased by 0.015, this one will decrease by 0.015. And if you subtract that, that should give you 0.01 moles of your KOH. And so now this is what happened. Because you combine the two solutions, this is the reaction that occurred, and as a result, it resulted in the strong acid running out and the strong base going down to this number, this moles in amount. And also the reason why I didn't include H2O and KNO3 increasing, because H2O is not significant to the pH change, because H2O doesn't change the pH. And KNO3 are spectator ions. Remember SNAP? Because it's SNAP, and also it's SNAP, it doesn't really affect the pH either. So that's why they're not considered. And so as a result, this at the combined solution, this is what's ever left of the reactants. This being, there's only the strong base left. And so because you have only the strong base left over, now you have the OH and you have the moles. What you want to do is convert it back to concentration and then get the POH. So let's do that. If you recall from earlier, if I scroll back up, it says that the combined solution has a total volume of 800. This is very important, guys. So because you had 300 earlier and 500 for each individual solution, you add it all together and that gave you 800. You can't use the old volumes because they don't work in this case anymore because you're at the combined version. So remember to get the total volume by adding the two solutions. And so now that you have 800 as your milliliters for the combined solution, I would just do this. So all I did was I used the moles that we got from before, and then I would divide by the volume of our combined container, that being 0.8 liters. Remember, convert to liters, and it will give me this concentration. And so now that we have the concentration of KOH, remember, because it's fully ionizing, you can just say that since KOH breaks into K plus and OH minus, the concentration is 1 to 1 with the compound, and so the concentration of the compound equals OH minus as well. So now we have the concentration of the OH minus, and now what you can do is pretty whatever you use whatever method you want to find the pH. And so the one that I usually like to do is using finding the POH first, and then using this equation to find the pH. So how I would do it is take the negative log of the concentration I found for the OH minus. It would give me approximately 2.903, and then what I would do is I would subtract 2.903 on both sides, and then that will eventually give me to like 11.1. Oh, that was awful. Wait 1 second. It gives me 11.1 equals pH. And so now, as we scroll back up, notice that 11.1 is D. Okay, So just as a breakdown on how to do this again, whenever you have two solutions and you're combining them together, firstly, make sure that if there's a strong substance, it can be either the acid or the base, it's a one-way reaction. So you're not using concentration anymore, you're using moles. So find the moles, then you would find the limiting reagent. And so using the limiting reagent, because you're decreasing the reactants as you proceed, the limiting reagent just decreases all the reactants by that number. And so that decreases the limiting reagent to 0, and then the other one to whatever's left over, and use the leftover amount of the other reactant, that being the base of the acid, and that gives you um, basically a hint to the moles of the base or the acid. Then, because you have this is the result of the combined solution, you want to use the moles here and then divide by the volume of the combined solution to get the molarity. And then if it's weak or strong, you just find the OH minus and then use your unit 8 knowledge to find the rest. And so voila, hopefully that was helpful.